How many calculations do you think your graphics card performs every second while running video games with incredibly realistic graphics? Maybe 100 million? Well, 100 million calculations a second is what's required to run Mario 64 from 1996. We need more power, maybe 100 billion calculations a second. Well, then you would have a computer that could run Minecraft back in 2011. In order to run the most realistic video games such as Cyberpunk 2077, you need a graphics card that can perform around 36 trillion calculations a second. This is an unimaginably large number, so let's take a second to try to conceptualize it. Imagine doing a long multiplication problem once every second. Now let's say everyone on the planet does a similar type of calculation but with different numbers. To reach the equivalent computational power of this graphics card and its 36 trillion calculations a second, we would need about 4,400 Earths filled with people all working together and completing one calculation each every second. It's rather mind-boggling to think that a device can manage all these calculations. So in this video, we'll see how graphics cards work in two parts. First, we'll open up this graphics card and explore the different components inside, as well as the physical design and architecture of the GPU or graphics processing unit. Second, we'll explore the computational architecture and see how GPUs process mountains of data and why they are ideal for running video game graphics, Bitcoin mining, neural networks, and AI. So, stick around and let's jump right in. Before we dive into all the parts of the GPU, the difference between GPUs and CPUs, let's first understand the differences between GPUs and CPUs. Inside this graphics card, the graphics processing unit or GPU has over 10,000 cores. However, when we look at the CPU or central processing unit that's mounted to the motherboard, we find an integrated circuit or chip with only 24 cores. So, which one is more powerful? 10,000 is a lot more than 24. So you would think the GPU is more powerful. However, it's more complicated than that. A useful analogy is to think of a GPU as a massive cargo ship and a CPU as a jumbo jet airplane. The amount of cargo capacity is the amount of calculations and data that can be processed. And the speed of the ship or airplane is the rate at which how quickly those calculations and data are being processed. Essentially, it's a trade-off between a massive number of calculations that are executed at a slower rate versus a few calculations that can be performed at a much faster rate. Another key difference is that airplanes are a lot more flexible since they can carry passengers, packages, or containers and can take off and land at any one of tens of thousands of airports. Likewise, CPUs are flexible in that they can run a variety of programs and instructions. However, giant cargo ships carry only containers with bulk contents inside and are limited to traveling between ports. Similarly, GPUs are a lot less flexible than CPUs and can only run simple instructions like basic arithmetic. Additionally, GPUs can't run operating systems or interface with input devices or networks. This analogy isn't perfect, but it helps to answer the question of which is faster, a CPU or a GPU. Essentially, if you want to perform a set of calculations across mountains of data, then a GPU will be faster at completing the task. However, if you have a lot less data that needs to be evaluated quickly, then a CPU will be faster. Furthermore, if you need to run an operating system or support network connections and a wide range of different applications and hardware, then you'll want a CPU. We're planning a separate video on CPU architecture, so make sure to subscribe so you don't miss it. But let's now dive into this graphics card and see how it works. In the center GPU GA102 architecture of this graphics card is the printed circuit board or PCB with all the various components mounted on it. And we'll start by exploring the brains, which is the graphics processing unit or GPU. When we open it up, we find a large chip or die named GA102 built from 28.3 billion transistors. The majority of the area of the chip is taken up by the processing cores, which have a hierarchical organization. Specifically, the chip is divided into 7 graphics processing clusters or GPCs, and within each processing cluster are 12 streaming multiprocessors or SMS. Next, Inside each of these streaming multiprocessors are 4 warps and 1 ray tracing core. And then, inside each warp are 32 CUDA or shading cores and 1 tensor core. Across the entire GPU are 10752 CUDA cores, 336 tensor cores, and 84 ray tracing cores. These 3 types of cores execute all the calculations of the GPU, and each has a different function. CUDA cores can be thought of as simple binary calculators with an addition button, a multiply button, and a few others, and are used the most when running video games. Tensor cores are matrix multiplication and addition calculators, and are used for geometric transformations and working with neural networks and AI. And ray tracing cores are the largest but the fewest and are used to execute ray tracing algorithms. Now that we understand the computational resources inside this chip, one rather interesting GPU GA102 manufacturing fact is that the 3080, 3090, 3000, and 80T and 3090T graphics cards all use the same GA102 chip design for their GPU. This might be counterintuitive because they have different prices and were released in different years, but it's true. So, why is this? Well, during the manufacturing process, sometimes patterning errors, dust particles, or other manufacturing issues cause damage and create defective areas of the circuit, instead of throwing out the entire chip. Because of a small defect, engineers find the defective region and permanently isolate and deactivate the nearby circuitry. By having a GPU with a highly repetitive design, a small defect in one core only damages that particular streaming multiprocessor circuit and doesn't affect the other areas of the chip. As a result, these chips are tested and categorized or binned according to the number of defects. The 3090T graphics cards have flawless GA102 chips with all 10752 CUDA cores working properly. The 3090 has 10,496 cores working. The 3080T has 10,240 and the 3080 has 8,704 CUDA cores working, which is equivalent to having 16 damaged and deactivated streaming multiprocessors. Additionally, different graphics cards differ by their maximum clock speed and the quantity and generation of graphics memory that supports the GPU, which we'll explore in a little bit. Because we've been focusing on the physical architecture of this GA102 GPU chip, let's zoom into CUDA core design into one of these CUDA cores and see what it looks like. Inside this simple calculator is a layout of approximately 410,000 transistors. This section of 50,000 transistors performs the operation of a times B plus C, which is called fuse, multiply, and add, or FMA, and is the most common operation performed by graphics cards. Half of the CUDA cores execute FMA using 32-bit floating point numbers, which is essentially scientific notation, and the other half of the cores use either 32-bit integers or 32-bit floating point numbers. Other sections of this core accommodate negative numbers and perform other simple functions like bit shifting and bit masking, as well as collecting and queuing the incoming instructions and operands, and then accumulating and outputting the results. As a result, this single core is just a simple calculator with a limited number of functions. This calculator completes one multiply and one add operation each clock cycle, and therefore with this 3090 graphics cards and its 10,496 cores and 1.7 GHz clock, we get 35.6 trillion calculations a second. However, if you're wondering how the GPU handles more complicated operations like division, square root, and trigonometric functions, well, these calculator operations are performed by the special function units, which are far fewer, as only 4 of them can be found in each streaming multiprocessor. Now that we have an understanding of what's inside a single core, let's zoom out and take a look at the other sections of the GA102 chip. Around the edge, we find 12 graphics memory controllers, the NVLink controllers, and the PCIe interface. On the bottom is a 6 MB level 2 SM memory cache, and here's the GigaThread engine, which manages all the graphics processing clusters and streaming multiprocessors inside. Now that we've explored this GA102 GPU's physical architecture, let's zoom out and take a look at graphics card components, the other parts inside the graphics card. On this side are the various ports for the displays to be plugged into. On the other side is the incoming 12-volt power connector, And then here are the PCIe pins that plug into the motherboard. On the PCB, the majority of the smaller components constitute the voltage regulator module, which takes the incoming 12 volts and converts it to 1.1 volts and supplies hundreds of watts of power to the GPU. Because all this power heats up the GPU, most of the weight of the graphics card is in the form of a heat sink with 4 heat pipes that carry heat from the GPU and memory chips to the radiator fins, where fans then help to remove the heat. Perhaps some of the most important components, aside from the GPU, graphics memory GDDR6X, GDDR7 are the 24 gigabytes of graphics memory chips, which are technically called GDDR6X SDRAM, and were manufactured by Micron. Learning something new today. Make sure to subscribe to the channel and tap the notification bell so you never miss a lesson. We're here to make complex topics simple, and your support helps us keep creating quality educational content just for you. Thanks for being part of the journey. See you in the next video.